You're welcome to Educational World Selaxi. Thank you for tuning in. So this is my own NECO Physics Practical number 1 prediction question. Now the diagram you are seeing there is how the setup supposed to be. Okay, now before I proceed, there are things you need to know about this experiment that only NECO has the jurisdiction, and those are the distance or the length of the meter rule that will be projected away from the table. That is number 1. Secondly, the position where the mass hanger will be hung. That's position N, as you can see from the diagram. And also, NECO has the jurisdiction, only NECO has the jurisdiction to determine what we are going to evaluate. So, but this experiment is based on relative density. So that is why I wrote out to evaluate U, which is equal to the length in air, and V, which is the length in water. And when we plot the graph of U against V, that thing will be the slope will give rise to the relative density of the masses. Okay, so when you set up the apparatus as shown in the diagram, so the first thing we have to do here is to record the distance L0 when the mass hanger has not been hung at the position N. Then we take the distance L0. Then when we hang the mass hanger, we take the distance L1. L1 is distance in air, and we put it inside water and get the distance in water. We repeat the experiment again for other values of masses, 100, 150, 200, and 250, and evaluate for the length in air and length in water. Then we will now plot a graph of U against V, which represents the relative density of the substance. Okay, and we'll find the slope of the graph. So this is what this experiment is all about. There may be several variations, but just know that it is the same setup. So once you know how to set this experiment up and perform the practical, forget about what NECO will bring out. Okay, don't forget to like, share, and subscribe if this video is informative and educative. Okay, so let's, without much ado, move into the practical at once. These are the set of apparatus given to us for the NECO Physics Practical number 1. So here we have our rotor stand. Here we have 2 meter rule. 2 meter rule. We have optical pin. We have a mass hanger. This is a mass hanger, a 50-gram mass hanger. And we have 4 set of masses, 50-gram set of masses. There are 4. 1, 2, 3, and 4. We have our G clamp. We have water with beaker. And we are asked to bring a plasticine. Plasticine is a sellotape to hold the optical pin in position, but I will improvise it with a ruler. So the next thing is to attach our meter rule and clamp it on the table such that half of the meter rule is projected outwards, as you can see. Now I improvised and used rope to hold my optical pin in position, as you can see. All right, so now the other meter rule, I clamped it on a clamp, and I'm taking my readings from this other graduation. As you can see, that is where I'll be taking my readings from, and taking the first reading when no mass is hung on the rule. I have it to be 62.0. that is my LO. My L naught is 62.0. no mass is hung now. All right, so this is my practical setup. As you can see, the apparatus is well set up as indicated in the diagram. Now let's go to the practical procedure. So I attach the 50-gram mass hanger at the 10 cm mark of the meter rule and check the reading there. Now the reading is giving me 64.4. I record it down. When I place it inside water, now the new reading indicated by the pointer is 64.2. 64.2. As you can see, 64.2. I take the reading down. Okay, now I have to add another mass, another 50-gram mass to make it 100-gram mass. So I place it inside water and make sure that it's completely immersed in water. Then I now check for the reading. Make sure before you take your reading that the oscillation of the mass has ceased. So taking my reading, I have that the reading in water is exactly 66.0. You will see that 66.0. Meanwhile, I have performed this in air when the mass was not in water and the value was giving me 66.50. So also take note of that. It was 66 or 66.50 in air. All right, so adding extra 50-gram mass to make it 150 grams and preventing the mass from oscillating with my hand. So I'm going to check the pointer reading. Checking the pointer reading now, the result is giving me 68.6. As you can see from the diagram there, 68.6. 68.6. So the next thing I'm going to do now, I'm going to place the mass inside the beaker of water, making sure that it is completely immersed in water, and I will take my reading. And taking my reading there gives me 67.90, which is approximately 68. As you can see, 67.9. Okay, so the next thing I'm going to do now is to add an extra 50-gram mass to the 150 to make it 200 grams. And after that, I'll prevent the mass from oscillating and check the reading on the meter rule. And the reading on the meter rule is giving me 70.9. 70.90. Okay, so that is that. So when I place it inside the beaker of water, as you can see, making sure that it's completely immersed in the beaker of water, and I take the reading, the new reading now from the meter rule. Okay, what is it going to give us? So checking the reading at the meter rule. Okay, so we have our new reading as 70.0 at the dot. 70.0 at the dot. 70.0 at the dot. Okay, so the next thing to do now is to add an extra 50-gram mass to the already 200 grams to make it 250. And after doing that, now I will now prevent the mass from oscillating and check the reading on the meter rule. So checking the reading on the meter rule, we have our value to be 73.3 centimeters. So we take that down. That's the weight in air. All right, so we now place it inside the beaker of water, as you can see. Now checking the new reading there on the meter rule. See, the reading on the meter rule now is 72.2. So that's that. We'll form our table of values and then go to graph plotting. So now this is our table of values. As you can see, the uniform number of decimal placements, and the table has their respective units. So without much ado, we are going to go into the graph plotting immediately to save our time. So for the graph plotting, this is a graph of U against V, and the scale used here is 2 cm to represent 2 units on the vertical axis and 2 cm to represent 3 units on the horizontal axis. So you can set from the vertical axis, you can see 2, 4, 6, 8, 10, 12 units. That's 2 cm to represent 2 units. While on the horizontal axis, you can see 3, 6, 9, 12, 15. That's 2 cm to represent 3 units. So we plot our points. Okay, when V is 2.2, U is 2.4, we mark out the points. Secondly, when V is 4.0, U is 4.5 centimeters, we mark out the points as well. So we move to when V is 5.9 centimeters, U is 6.6. Also, when V is 8 centimeters, U is 8.9. And lastly, when V is 10.2 centimeters, U is 11.3 cm. So we plot the points with a straight line, and that is our graph. Remember the graph, or this is a graph of U against V, and the slope of this graph, what does it represent? What is its significance? Like I said, it signifies the relative density. So slope is usually change in the vertical axis over change in the horizontal axis. So change in U over change in V. And the 2 points here is 11.3 minus 3.0 and 10.2 minus 2.6. Now evaluating that with the help of our calculator, we have 8.3 all over 7.6, which gives us 1.09. So this is relative density. It has no unit. It has no unit. So why is this relative density? You know, the length or the depression of the meter rule is a function of the weight or the mass of the yes, it's a function of the mass hung. So that means that length is proportional to the mass. You know, relative density is weight in air over weight in water. So length in air over length in water gives us relative density. So that's the main aim of this practical. All right, so talking about the precautions, remember that the masses were not oscillating and the table was steady before you take your readings. Thank you.